Dear students, today's topic of my lecture, Ray Optics, Chapter 9, Part 4. So just see that what you have to learn in the Part 4 of Ray Optics. First, you learn thin lens formula, then linear magnification, power of a lens. After that, combination of thin lenses in contact. One by one I explain. So before explaining to the thin lens formula, I just remind few important things. The first one is the first principal focus. So you understand what is the meaning of the first principal focus? First principal focus is a point on the principal axis of the lens at which if an object is placed, the image would be formed at infinity. So you see here in case of the convex lens as well as in case of concave lens. So here it is F1 is the first principal focus. So object is placed at the focus. So image is formed at infinite. Similarly, in case of the concave lens, now second principal focus means the second principal is the point on the principal axis of the lens at which image is formed when the object is kept infinity. Then that point is known as second principal focus. So ray diagram you see that here. The object is infinite, then image is formed at the infinity. So it is represented by F2. So F2 is the representation of second principal focus. F1 is the representation of first principal focus. Similarly, in case of the concave lens, we can see it. And the distance between the optical center and the principal focus, that is called focal length. Now I will explain thin lens formula. So first we take convex lens, and in it there are two parts. One is the real image, another one is virtual image. In both the cases the formula remains the same, and let us see first ray diagram. So it is a convex lens. C is the optical center. This is the principal axis. F1, F2 are the first principal focus and second principal focus. Similarly on both the sides, 2F1 and 2F2. Now we place an object AB between F1 and 2F1, and then first ray from the point A, always parallel to the principal axis, incident onto the lens, and after that refracted and passes through the second principal focus, and second ray that passes to the optical center and meet to the first refracted ray, which is form a real image. And you see that it's a ray diagram like that. So A dash is the real image of the point A. Now we drop a perpendicular on principal axis, that is A dash B dash. So A dash B dash is the real, inverted and magnified image. Now you see that U is the representation of the object distance, V is the image distance, F focal length of the convex lens, R radius of curvature. Now how we can derive the formula? For that purpose we take the triangles ABC and A dash B dash C. A, B, C and A dash B dash C. They are the similar triangles. So we use the property of the similar triangle. We can write A dash B dash upon AB equal to CB dash upon CB. Similarly, we take another triangles TCF2 and A dash B dash F2. They are also the similar triangle. So same way we can say that A dash B dash upon DC equal to B dash F2 upon CF2. So mark these equations. This one is equation 1 and this equation is 2. Now you see in the diagram this DC is equal to AB. So in equation 2 in place of DC we have to write AB. So you will get A dash B dash upon AB equal to B dash F2 upon CF2. Then you see that from equation 1 and 3 their left hand sides are equal. So right hand sides can be made equal. So CB dash upon CB equal to B dash F2 upon CF2. Now this B dash F2 can be written as CB dash minus CF2 because all distances that we have to measure from optical center. So that's why we have to write B dash F2 in terms of CB dash minus CF2. So substitute this. So you will get CB dash upon CB equal to CB dash minus CF2 upon CF2. Mark this equation number 4. Now with the help of the new Cartesian coordinates, we have to put the values CB dash image distance which is in the direction of the incident ray. So it is positive, that is plus V. CB minus U. Similarly CF2 it is plus F. Remember it, the focal length of the convex lens is always positive. Substitute this value in equation number 4, then it becomes V upon minus U equal to V minus F upon F. Then you cross multiply it and simplify. Then you will get Vf equal to minus Uv plus Uf. Divide both sides by UVF. Then you will get U. This Vf and this Vf get cancelled. This UV and UV get cancelled. This UF get cancelled. So what you have? 1 upon U equal to minus 1 upon F plus 1 upon V. Now rearrange it. Then 1 upon F equal to 1 upon V minus 1 upon U. Similarly, we can find out in case of virtual image. That is, we are taking a convex lens and the virtual image. The ray diagram is shown here. Object is placed between the optical center and focus, that is AB. The first ray is parallel to the principal axis and after refraction it passes to the second principal focus F2. The second ray that passes to the optical center from point A, but two refracted rays are not meeting, and we extend it in the back direction represented by the dotted lines. Then it appears to come from A dash point. Then A dash is the virtual image of the point A. Then drop a perpendicular on principal axis, that is A dash B dash. Then this A dash B dash is the virtual, erect and magnified image of object AB. And the same concept that we have to apply and find out the formula, the similar formula we get 1 upon F equal to 1 upon V minus 1 upon U. In the same way, we can also find out the formula for concave lens, and in that concave lens the image is always formed virtual. So you see that the ray diagram here, the object is AB. So first ray from the point A is parallel to the principal axis and get refracted, that is diverge, and the second ray which passes to the optical center, but the two refracted rays are not meeting. So that's why we extend the first refracted ray on back direction, that I am representing by these dotted red lines. Then the A dash B dash, that becomes the virtual image of the object AB. So A dash B dash is virtual, erect, diminished. And same concept we apply and find the formula which comes 1 upon F equal to 1 upon V minus 1 upon U. Now the linear magnification. In linear magnification, we can say that it is defined as the ratio of the size of the image to the size of the object. It is represented by small m, and small m equal to size of image upon size of object. And if we say that the image of the size is represented by h2 and size of the object is represented by h1, then this becomes h2 upon h1. And from the lens formula derivation, we know that a dash b dash upon ab equal to cb dash upon cb. Then a dash b dash is the image, so we are writing it is h2, and object is ab and it is h1. So then formula that we can write m equal to h2 upon h1 equal to a dash b dash upon ab equal to cb dash upon cb. Now for convex lens, in case of the real image, The image is inverted, so that's why H2 is minus H2, and object AB is erect, so it is plus H1. Now equal to A dash B dash upon AB, and CB dash upon CB equal to CB dash image distance, which is in the direction of incident ray, so it is plus V, object distance, which is in opposite direction to the incident ray, so minus U. So in that case the linear magnification is negative. But in case of the virtual image, both object and image are erect, so that's why both are positive. So m equal to plus h2 upon plus h1 equal to a dash b dash upon ab equal to cb dash upon cb. Both object and image distances are in opposite direction to the incident ray, so that's why minus v upon minus u, that is v upon u. So m is positive. So in case of the virtual image of convex lens, m is positive. Now we can similarly find out for the concave lens. Always the image is virtual. So m equal to h2 upon h1, because image and object both are erect, equal to a dash b dash upon ab equal to cb dash upon cb. Both image and object distance are in opposite direction to the incident ray. So that's why minus v upon minus u equal to v upon u. So m is positive. So remember it, in case of the virtual image, either it is for a convex lens or a concave lens, linear magnification is positive. But in case of the real image, linear magnification is negative. There are two more formulas of the linear magnification, that is in terms of the V and F. The first one is m equal to F minus V upon F, and in terms of U and F, m equal to F upon F minus U. And these two formulas you can find out by using the lens formula, 1 upon F equal to 1 upon V minus 1 upon U. So on both the sides you multiplied by V when you are going to find out the magnification in terms of V and F, and multiplied by U if you are finding the formula in terms of U and F. And finally you will get these formulas. So remember it. Now power of a lens. Power of a lens is basically defined as the tangent of the angle by which it converges or diverges a beam of light falling at unit distance from optical center. So you can see here we are taking a convex lens, and a ray of light that incident on this convex lens, after refraction it passes to the focus, but it deviates from its original path by certain angle, say delta. If this angle is delta, then this angle is also delta, and dc we are representing by h, which is basically equal to 1, which we are saying in the definition, unit distance from the optical center, and cf distance is focal length. Now then in the triangle cdf we find out tan delta, which is equal to perpendicular upon base dc upon cf, but dc is h, cf is f, so that's why tan delta equal to h upon f. If h equal to 1 as per definition, and tan delta equal to 1 upon f, which is equal to the power of lens. So thus we can say that power of a lens is the ability to bend a ray of light falling on it and is reciprocal of its focal length. Mathematically we can write P equal to 1 upon f. SI unit of power of lens is diopter, that is 1d. D is the representation of diopter, which is capital D. So 1d equal to 1 meter inverse. Thus power of a lens of focal length of 1 meter is 1 diopter. Power of lens is positive in case of the convex lens or converging lens, and it is negative for concave lens or diverging lens. So this is about power of a lens. Now two thin lenses in contact. So first case we take, both the lenses are convex. Here we are considering two thin lenses L1 and L2 of focal length f1 and f2 placed in contact with each other, as you can see in the diagram. C1 and C2 are the optical centers of the lenses L1 and L2 respectively. Suppose the point object is placed at point O on the principal axis. Then the first ray that passes from point object incident normally onto the lenses and passes straight. And the second ray which incident onto the lens L1. At this time there is no lens L2, then it passes after refraction represented by dotted line and form the real image I dash onto the principal axis. But when we place the second lens L2, then the ray which is refracted from L1, it incident on L2 and get further refracted and meet at point I. So I is the final real image of the point object O, and for this final real image I dash is the virtual object. Now for lens L1, OC1 equal to U and C1 I dash equal to V dash, which is represented here. Then from the lens formula, 1 upon V dash minus 1 upon U equal to 1 upon F1. F1, F2 are the focal length of the lenses L1 and L2. Similarly, for the second lens L2, U equal to C1 I dash equal to C1 I dash equal to plus V dash. That is the virtual object. Then C2 I equal to V. Then by using the lens formula, 1 upon V minus 1 upon V dash equal to 1 upon F2. Mark this equation 2. Now adding the equation 1 and 2, we get 1 upon V minus 1 upon U equal to 1 upon F1 plus 1 upon F2. In it, when we are adding, then 1 upon V dash gets cancelled. Then mark this equation number 3. If a single lens of focal length f produces the image I of the object as the two lenses L1 and L2 together do, then 1 upon V minus 1 upon U is equal to 1 upon F. Mark this equation number 4. Then in place of this 1 upon V minus 1 upon U, we can write this 1 upon F. So from equation 3 and 4, we get 1 upon F equal to 1 upon F1 plus 1 upon F2. That is F equal to F1 F2 upon F1 plus F2. Now if one lens is convex and other one is a concave lens, then in that condition, in case of the convex lens, focal length is positive, but in case of the concave lens, focal length is negative. So that's why the formula becomes 1 upon F equal to 1 upon F1 plus 1 upon minus F2 equal to 1 upon F1 minus 1 upon F2. Then we can say that F equal to F1 F2 upon F2 minus F1. Now three cases arises which are worth noting when one lens is convex and other one is concave. If f1 equal to f2, then in that case the focal length of the combination of this lens f equal to infinite. This means that combination would like to behave like a plain glass plate. Second point, if f1 greater than f2, then f is negative, therefore the combination acts as the concave lens. Third one is if f1 less than f2, then f is positive, therefore the combination would behave as a convex lens. Now some important points about the lenses in contact. The first one is when two thin lenses of focal length f1 and f2 are placed in contact with each other, then focal length of the combination is given by 1 upon f equal to 1 upon f1 plus 1 upon f2. Here you just note down, if one lens is convex and another one is concave, then you remember the sign conventions of focal length. In case of the convex lens, the focal length is always positive. In case of the concave lens, focal length is always negative. Now, if we say that P is the power of the combination and P1 and P2 be the power of the individual lenses, then P1 equal to 1 upon F1 and P2 equal to 1 upon F2 and P equal to 1 upon F. Then in that case, P equal to P1 plus P2. Thus the total power of number of lenses in contact is equal to algebraic sum of the powers of the individual lenses. Lenses are in contact are also used for increasing the magnification. So when the number of lenses are placed in contact, then each lens magnifies the image found by the preceding lens. Therefore, the total magnification M produced by combination is equal to the product of magnification produced by the individual lenses. That is M equal to M1 into M2 into M3 into so on. Fourth point, if two lenses of focal length f1 and f2 are separated by a finite distance d, then it can be proved that focal length f of the equivalent lens is given by 1 upon f equal to 1 upon f1 plus 1 upon f2 minus d upon f1 f2. Remember it. So if you like my video, like it, subscribe, press the bell icon. Stay safe, stay healthy, learn physics by my YouTube channel by staying at your home. Thank you and have a nice day.